So what I've got here then is a little patch antenna for 5.8 gigahertz FPV. It's from AOMWAY, however you pronounce that, AOMWAY, and it's a upgraded version from their previous one that people had a lot of bad reviews about. That one, they said it wasn't didn't work very well. But I've got this one in. This is apparently their new one. It's a 6 dBi patch antenna, so it's not a particularly powerful one, but they're probably right on the mark with saying this is 6 dBi. But it does apparently work over quite a large frequency range. Now the frequency range is 5.705 gigahertz to 5.945 gigahertz, so that's quite a large range, and it has a VSWR of 1.5. Now this one is right hand circular polarized, but it's got this quite shiny black solder mask on here, and I can't quite work out how they're doing that, so I think I'm going to have to try and strip this away so we can see where the traces go and how they're getting that right hand circular polarization on there. But before we start doing that, I thought I'll hook it up to the spectrum analyzer just to see what its frequency response is over that large bandwidth that they are claiming. And it's only a small antenna, as I say. It's on some semi-rigid coax here, so let's hook it up and take a look and see how well it performs over 5.8 gigahertz. So I've got the little patch antenna set up, as you can see here, directional coupler. I'm feeding in a sweeping signal from 3.8 gigahertz to 8.5 gigahertz, and I'm feeding off here into the spectrum analyzer. I've got the patch antenna pointed down, so I'm not interfering with it too much over the top of it here, and here it is on the spectrum analyzer. So I've got the spectrum analyzer centered on 5.8 gigahertz here, and we've got two very nice frequency responses here and here. This is the best one, and then we've got this one over here. Now this good one over here, this would be around the 5.7 gigahertz mark, and this one here will be about 5.95 gigahertz over here. And then we've got this curve here, this quite large curve, and again, this is a frequency drop, so it's going to be responsive in this area here. This is 5.8 gigahertz here, and this will be 5.9 gigahertz. So really you're mostly interested in what's going off in this section here. Most transmitters work around that frequency, 5.8 gigahertz to 5.9 gigahertz, although some do go down a little bit more. But you can see the frequency response here is quite poor. I mean, this is the baseline across here, and this is the drop, so it doesn't exactly perform well around this area here. It performs best down here, and then it performs well again up here. So if I track the spectrum analyzer back, this should be around the 5.7 gigahertz around here. So I've got the line now centered on 5.7 gigahertz, and as you can see, it's spot on to that really good first frequency response there. So if you're operating your transmitter in the 5.8 gigahertz frequency range, then you're not going to get good performance from this. If you operated a transmitter, which I'm not sure is legal in most countries, at 5.7 gigahertz, then you're going to get an excellent frequency response, and this antenna will perform really well. But because most people use it at 5.8 gigahertz, 5.845 gigahertz, you're not going to get the same performance from there. Now this antenna also claims a VSWR of 1.5. now I can tell you that that's not 1.5 across the band here. They've taken the best measurement, and the best measurement will be here at 5.7 gigahertz. The VSWR of 1.5 will not be 1.5 in the rest of the band. It will not even be 1.5 here at this second frequency response. So they're not really being truthful there. I think what a lot of manufacturers should state is, say, an average VSWR when they're making something that's such a wide band operating antenna. So the manufacturers are saying that the specifications for this little patch antenna are extremely broadband in that it'll work over such a large frequency range. They're saying that it works from 5.7 gigahertz up to they claim just below 6 gigahertz, around 7.50 gigahertz, but it's not, and they shouldn't be claiming that it is. Yes, it's still got a low frequency response here at the top at its main peak, but this is in the area that most people will use at say 5.840 gigahertz, for instance. You know, all around that little area they use quite a large band of the spectrum, and it does not work well at all in this area. And there's also a danger here, because the VSWR that they're claiming is coming from this first frequency response here, the 1.5. There is no way that this is the same across all the range of the frequency response of this antenna, and even here in the second frequency response is going to be a little bit higher than that. And the danger of using an antenna in a frequency area that has a significantly higher VSWR, say in this area, is I've got a 4 watt amplifier here in the lab that's for FPV. Now if you use this antenna with that 4 watt amplifier, you're going to get a lot of you know, reflections back down the transmission line, which can seriously damage equipment when you start putting a lot of power through it. You know, all that RF being reflected back down the line because it's not matched properly and it's got a high VSWR, so you can potentially end up damaging your equipment, your amplifier and your transmitter. So really they're stretching the truth here by saying it's a broadband antenna, because it's not, and they're stretching the truth with the VSWR as well. If they're claiming that this is a broadband antenna that works across all this frequency here, then they should be giving you an average of the VSWR. And if it is a broadband antenna that works across these two frequencies, then this should be a lot lower. It should look, say, something like this, a lot lower. You can't get a perfect you know, V-shaped like this over such a large area. It is very difficult, especially with a patch antenna, but you can get multiple frequency responses over that area, and then you can say that it's a quite a broadband antenna. So as we've just seen on the spectrum analyzer, you know, if you're going to use this in the 5.8 gigahertz frequencies, the performance from this is going to be absolutely dire. So I think what we'll do now is try and remove this solder mask here, so we can get a better idea of how they're achieving this right hand circular polarization. Now normally acetone is good for removing this solder mask, but I haven't got any, so I'm going to try and do it with a cotton bud and some paint stripper and see if I can get it off that way. I've got no intentions of ever using this antenna again, so if I do destroy it I'm not too bothered about that, but I'd like to see how they're achieving this claimed circular polarization. So I managed to get a great deal of the solder mask off on the area that we're most concerned about then. The paint stripper didn't do too good a job. I had to go out and get some acetone, and even that I had to remove quite a bit of the top layer of the solder mask so the acetone could do its work. But as you can see here, we can see what's going on now. So what we've got here then, we've got the signal being fed here, and then it branches off into two along these two transmission lines here. Although when it's like this on a PCB, it's called a microstrip line, but it's branching off here and here, and this passive part here, this L shape, it's not touching the transmission line here, but because it's so close, it's affecting the signal on that line, so it's slowing it down slightly. So this side is getting the feed a lot quicker than this side, and that's how they're achieving the circular polarization. This is right hand circular polarization. It's going in a clockwise motion. Because it's faster on this side and slower on this side, we're getting that circular polarization working there. So it's really a very very simple design, and there will be a certain amount of loss with this method as well, because you get some of that signal traveling up and then dissipating out of here. So you know, that's a little bit of loss there, and with this only being a small 6 dBi antenna, we're getting a little bit of loss from there. So you know, it's not a very efficient method, and you know, any kind of helical really will perform much better than this. But they have designed it correctly, and I mean, you may notice there's no right hand corners on this strip line here or here, because right hand corners on a strip line when you're designing something like that are a bad idea, because a right hand corner will automatically by design become an antenna, so you'll have even more loss. So we've got nice you know, cut-offs to the right angled corners here, and here as well on the feed line it's cut off here going down onto the feed signal wire here. So it's designed well, but you know, it just doesn't work well at the frequency you would expect it to work at. And as I say, because it's only a small 6 dBi, and this will give it a certain amount of loss as well, it just wouldn't be a very strong performer at all. So to sum up then, what we've got here is an antenna that is pretty well made, I have to say. You know, you can't knock the construction techniques, but it's just not going to work for you at 5.8 gigahertz. It's just not going to perform well at all. And they are stretching the truth a little bit by saying, you know, the VSWR is 1.5. They should really have an average over the you know, advertised range that they are claiming that this works at, but they would never do that, because then they would have to advertise a pretty poor VSWR figure. And you know, as I say, if you're wanting to use this at 5.8 gigahertz, it's just not going to perform, because the two best frequency responses are below that and above that. So I would give this one a miss. So I hope you found this video useful. It's a little bit different. I don't think anybody else is testing this type of antenna by using a spectrum analyzer and looking at it that way. I mean, you can test this by sticking it on a quadcopter and seeing how far you can go before you start getting a grainy signal or the signal drops out. But as far as using a spectrum analyzer or a network analyzer to test these things, I don't think anybody else is actually doing it. And what I'm finding with a lot of this stuff is it really is a little bit hit and miss, the quality and performance that you can get by using some of this. I mean, sometimes you can pick up something really cheap and drop on, but most of the time you pick up something really cheap and it's just cheap. So as I say, if you did enjoy it, then please give it a thumbs up. Any comments or questions, if you've got one of these and you're happy with it, then please you know, let us know in the comments. But as I say, you know, as you've seen on the spectrum analyzer, it just isn't going to perform well at all at 5.8 gigahertz. I mean, yes, it's got circular polarization, but you're probably better off using you know, a dipole antenna and a smaller dipole antenna on your quadcopter. I'm pretty sure if you had that set up, you'd get a lot better and longer range response from your setup than you would using this. So as I say, any comments, questions, drop them below. I'll do my best to answer them, and hopefully you'll join me on the next one.